Hello, hello, 11 Chem. In this video, we're looking at the echalk.co.uk 3D models of carbon allotropes. Now, an allotrope is an element that exists in multiple different forms. Carbon is a very good example of this because it exists as graphite, it exists as diamond, and there are several other forms of carbon that you can prepare synthetically, like carbon nanotubes, buckyballs, which I'll show you in a second, that you can prepare synthetically in a lab that can actually have carbon in different configurations. Now, by modifying the structure of the materials, you modify their properties. So, pictured on the screen just here is the echalk webpage. It will attempt to use Flash, and when Flash is not detected in a modern browser, it'll switch to HTML5. Okay, so you should be able to get this working regardless. All right, what it is a 3D model that you can left click on and drag around, and a drop-down box with a variety of different carbon allotrope models that you can select. Okay, shown here is graphite. Now, what you can see is the classic six-sided ring of carbon. All right, and you can see that the carbon is arranged in sheets. One of the reasons why graphite is actually used by locksmiths is because these sheets of carbon slide over each other really easily. All right. Another reason why graphite is conductive, if you have a look at each of these carbon atoms, each carbon is only bonded to 3 other carbons. Carbon's got 4 electrons, guys. So that means there's a spare electron on each carbon. So there's 3 electrons in this structure. It's quite unusual for a structure made up of non-metals. All right, let's take a look at diamond. A diamond unit cell. This is a small cut through of diamond. All right, you can actually see the tetrahedral shape around the central carbon I have just here. All right, we'll go to the large scale. You actually see the way in which diamond has carbon arranged in a network structure, a full 3D network structure where each carbon atom is arranged in a tetrahedral network. Okay, it's part of the reason why diamond is so hard is because all of that structure is bonded together in one big massive covalent network. Let's take a look at some of the more exotic arrangements. This is called a Buckminster Fullerene, or a buckyball. All right, notice you have your carbon atoms. They're arranged in ring structures with double or single bonds, and this structure has either pentagons or hexagons, and it's literally a soccer ball made out of carbon atoms. All right, these are interesting macromolecules, large molecules. All right, one of the things that they can be used for is a lubricant, all right, because they will roll, all right, on a molecular scale. And one of the things that they're potentially very interesting for their usage would be to actually put functional groups, different atoms attached to the carbons on the surface. All right, so this will be attracted to different materials. All right, imagine if you were to, say, have it attracted to lung tissue and you were able to somehow put a anti-cancer drug inside this, and we're able to get it to selectively go to a particular type of tissue or selectively stick to a particular surface. There's a lot of engineering and medical potential. All right, that's the carbon-60 version of a Buckminster Fullerene. There are other versions of Buckminster Fullerenes. This is carbon-70. All right, notice there's a bit of a different arrangement, and it's not spherical. It's a bit of like an egg shape. All right, still works quite well as a lubricant. All right, and there are carbon nanotubes. All right, here's a short model of one just here. Now, these are a really interesting material. we have our carbon arranged in such a way that we have 6-sided rings of carbon. With each carbon, it's basically a sheet of graphite that has been bent around into a tube. All right, has really promising mechanical properties. All right, effectively, if you could get these long enough, they would have a higher strength to weight ratio than steel. All right, now, of course, getting them long is a big engineering challenge. All right, but there's no reason why you can't have a rope made out of a plastic-like material, a polymer material, that has these structures embedded within it. They can be quite short, but as a composite material, it can be quite strong. Okay. I'll look at a long version of that. In our activity we're doing today, you are going to look at a bunch of different carbon allotropes. Okay, and look at the arrangement of atoms within them, how many bonds are going to each carbon. All right, and I suggest you do some research, in particular on the Buckminster Fullerenes, or buckyballs for short, and the carbon nanotubes and their properties, because they are quite interesting. Thank you for watching the video, Year 11. Let's get on with the lesson. Bye-bye.